The goal of this webinar is to present the fundamentals of RISC-V so that you're comfortable taking the first steps. We'll also cover where exactly to find additional information which is not covered in this webinar. This webinar is the first in a three-part series that'll take you on a journey from understanding the fundamentals of the RISC-V architecture. And then the second webinar will introduce you to SiFive's own RISC-V-based Coreplex IP. And then the third webinar will actually walk through evaluating SiFive's Coreplex IP. As you may have discovered, your line is currently on mute. However, you are still able to ask questions via the question and answer box highlighted in the screenshot in red. We have a number of panelists standing by who can help answer those questions live. So please don't wait till the end to ask questions. Also, this webinar is being recorded and we'll have the slides as well as the video on our website soon. To kick things off, I would like to invite Krista Asanovic to present an introduction to RISC-V. Krista is the co-creator of RISC-V as well as a co-founder of SiFive.
Hi, welcome to the webinar. So I just want to give you a quick introduction to RISC-V in terms of where it came from. So I'm also a professor at UC Berkeley, and back in 2010, we were starting a whole bunch of new research projects at Berkeley, and for every architecture research project, you need to pick an ISA. And when we looked around the industry, the commercial ISAs we found were just too complicated. For unnecessary reasons. They were just needlessly complicated. And also, perhaps more importantly, there were serious IP legal issues around those ISAs. If we wanted to build designs and cores and share them with our friends in academia, we weren't allowed to because of the IP constraints. So that motivated us to come up with a clean slate RISC-V design that we could use as our own research projects. And then we started building a bunch of stuff around it. An interesting thing happened is we realized that people outside were using the RISC-V design that we'd put out on the web and were starting to ask us questions about what was going on with it and why was it changing and so on. And so we decided it was time to get a bit more serious about it. So in May 2014, we released a full user level spec, version 2.0, and that's still a current standard. The idea is to freeze the spec and not change it. So the user level spec is frozen at version 2, released in May 2014. The privileged architecture that is related to how you run Unix and other operating systems, that's currently at version 1.10. And the idea is that 1.10 from now on, the privileged architecture should be backwards compatible with version 1.10. So we produced this ISA spec. We made it all available under a permissive BSD style license. One thing to be clear about RISC-V, it's not a company and it's not a particular CPU implementation. It's designed as a standard specification that provides an interface between software and hardware. And so the goal of RISC-V is really that many companies can implement RISC-V cores, and they don't have to be open source. You can have proprietary RISC-V cores as well as open source RISC-V cores. But the whole software community can build the ecosystem around a single standard ISA. And so any of these core implementations should be able to run the whole software stack. So next slide. So as we created RISC-V and pushed it out there, some of the feedback we got from industry who were keen to use it was there really needs to be a longer-lived organization rather than just UC Berkeley to manage this ISA. And so back in August 2015, I created this RISC-V Foundation as a nonprofit trade association. It's similar to the Linux Foundation, and its goal is just to manage, to standardize, protect, and promote the free and open RISC-V ISA. And it's grown at an incredible rate. So now we have over 65 member companies in a wide range of markets. And these include some of the biggest names in the computing industry, members already, and actively working on RISC-V. And the way the foundation works is they're in charge of the standard, and it creates working groups that guide future development of the architecture. So unlike the other proprietary industry ISAs, the development of future extensions is done out in the open as part of the foundation working groups. And so there's a lot of activity now to design various extensions on top of the base RISC-V ISA. So it's a very actively and community developed instruction set, and it's getting this wide adoption across the whole industry. And now I'll hand you back to Drew to tell you about, go through more details of RISC-V and later tell you about what SiFive is building.
Thanks, Krista. That was a great introduction to RISC-V. So to start off, we'll cover the basics. So RISC-V defines a standard naming convention which is used to describe the exact ISA of a given implementation. And so the naming format of RISC-V instruction sets are as follows. So the first two letters are R and V, and these stand for, indicate that it's going to be a RISC-V architecture. Following RV is a number, and that number is used to indicate the width of the integer register file as well as the size of the user address space. And so the acceptable numbers here are 32, 64, and 128. Following this number is a string of letters which is used to indicate the extension supported by a given implementation. And so an example of a complete ISA name would be RV64GC. And so we don't know what GC stands for just yet, but right off the bat, we can see that this is going to be a 64-bit RISC-V implementation. So as part of the RISC-V specification, it defines extensions, and extensions are a means of adding instructions to the architecture. The base extension is I, which stands for integer, and the I extension is the only required extension in a given RISC-V implementation. So the I extension defines a set of integer instructions. In addition to standard extensions, RISC-V allows for non-standard extensions, which are going to be specific to an implementation. And so standard extensions are added to the RISC-V specification and agreed upon by the RISC-V Foundation, whereas non-standard extensions are not. And so some examples of the most common standard extensions are in the table on the right. And so we already went over I for integer. There's also the M extension, which adds multiplication and division instructions. The A extension, which adds atomic instructions. The F and D extensions add support for single precision and double precision floating point instructions. The G extension is sort of a shorthand and indicates that a given implementation supports the I, M, A, F, and D extensions. Also, the C extension is another common one, and it stands for compressed. So it has 16-bit compressed instructions, and we have a section discussing that in a couple of slides. And so while the specification does not describe any non-standard extensions, it does describe how to describe those in the ISA name string. And the method for doing that is by specifying a capital X followed by the extension name. And so if we put all this together, RV32I ISA name is the most basic RISC-V implementation, is a 32-bit architecture that only supports the integer instruction set. RV32IMAC builds on that by adding the multiply, atomic, and compressed instructions. RV64GC, which is the name that we saw in the previous slides, adds the integer multiplication, atomic, single and double precision floating point, as well as the compressed instructions. And then an example of a non-standard extension is capital X followed by EXT, which would be the name of the non-standard extension, EXT. Next, we'll talk about the register file. So there are 32 integer registers in the RISC-V architecture. And if you implement a floating point extension, then there are 32 additional floating point registers. The width of the register file is determined by the ISA. So if it's RV32, it's 32-bit wide registers. If it's RV64, then it's 64-bit wide registers. The RISC-V specification also defines an application binary interface, or ABI, and this defines standard functions for registers. So for example, the calling convention for functions, the ABI defines which registers are used to pass arguments as well as return values. And this is important for software interoperability. So RISC-V compilers and software libraries all adhere to this ABI. And if you would like your particular application or code to be compatible with calling these registers or interworking with output of compilers, then simply following the ABI definition will give you that. And just to note that the GCC assembler accepts both register name formats, so the X register names as well as the ABI names. So for example, S0 or T1, for example. RISC-V modes. So RISC-V also defines 3 levels of privileges called mode. So from least privilege to most, level 0 is going to be user mode, level 1 is supervisor mode, and level 3 is machine mode. Machine mode is the only required mode to be implemented in a RISC-V implementation. And this is important because it allows for a range of targeted implementations. If you're building, for example, a small embedded core where you're in control of the entire software stack, you might not have the requirement for separate modes, in which case you can reduce complexity by only implementing a machine mode implementation. If you have a slightly more sophisticated implementation where maybe you have a real-time operating system, you might want to use 2 modes, in this case machine and user, in which your RTOS kernel would operate in machine mode and the operating system application code would operate in user mode. Also, for more sophisticated implementations still, such as those implementing Linux, you might want to implement all 3 levels of privilege, in which case you would implement machine, supervisor, and user modes. So the supported mode combinations are shown in the table on the bottom right. For example, you cannot implement a machine and supervisor only mode or a supervisor and user only mode. Machine and supervisor modes each have their own sets of control and status registers, and we'll talk more on these in a few slides. The RISC-V specification also defines a means of physical memory protection, and this can be used to enforce access restrictions on lesser privileged modes. So the classic example of this is if you have untrusted user mode software, you can restrict which memory regions that software has access to. So in the user mode context, for example, you might want to give the user mode software full read, write, and execute permissions. However, if there's shared library code, you might only want to give that user mode context execute only privileges of the library code so that it can't modify it. One neat feature of the RISC-V physical memory protection scheme is that it defines the ability to lock a region. And what makes a locked region different is that it enforces the access permissions on all modes, including machine mode accesses. So for example, let's say you have a super secure key that you want to read at boot time, but then prevent any reads happening thereafter. You could then lock the region, which will prevent any software, even machine mode software, from accessing that region. The only way to unlock a region is to reset the system. So the physical memory protection scheme defined by RISC-V supports up to 16 regions with a minimum region size of 4 bytes. So it's quite flexible in the amount of regions and size of those regions that it allows you to implement. RISC-V also implements support for virtual memory, and this is important for allowing sophisticated operating systems like Linux to operate. Virtual memory support does require a supervisor mode implementation, and you'll see why in a few slides. And it defines several different virtual memory modes. And so the first of those modes is called SV32. And so SV32 defines a 32-bit virtual address with 2 levels of page tables supporting 4 kilobyte and 4 megabyte pages. SV39 is another virtual memory mode. So SV39 requires a 64-bit RISC-V implementation, and it defines a 39-bit virtual address, as well as 3 levels of page tables, 4 kilobyte, 2 megabyte, and 1 gigabyte pages. And as you would expect, the page tables also contain access permission attributes, and these are all defined in the RISC-V privilege specification. Okay, moving on to RISC-V instructions. We are not going to cover every instruction in detail here. The idea is most, if not all of you, are using a compiler. However, we will go through some of the more interesting instructions. First, let's take a look at the RISC-V reference card. So the base extension, the integer extension, is described in the table on the left. And this shows all the instructions that it adds to the RISC-V architecture and that every RISC-V implementation is guaranteed to have. Adding a privilege mode adds 14 more instructions. And so if you implement the mandatory machine mode implementation, machine mode, privilege mode, then you will have these instructions as well, which are mainly used for reading and writing the control and status registers. The M extension adds support for integer multiply and divide instructions. The atomic extension adds 11 more instructions, and we'll cover these in a few slides. Floating point adds an additional 34 instructions for single, double, and quad precision floating point. And finally, the compressed extension adds an additional 46 instructions as well. And so this is the full instruction set reference card for an RV32GC implementation. And what's neat is that this does not only cover the 32-bit implementations, but it's also the same instructions for 64 and 128-bit implementations. Okay, let's take a look at the C extension, or the compressed instructions. So most of the compressed instructions, or most of the base I extension instructions compress to 16-bit equivalents. So the C extension introduces this 16-bit instruction format. And these are mainly one-to-one mapping of the standard integer instructions, meaning that the C extension does not define entirely new instructions, but rather a 16-bit encoding of the standard integer extension. So why is this important? It can be important for a number of reasons. If you're in the small embedded space, a smaller code size can directly result in reduced costs in an embedded system. If you think about a microcontroller, usually the cost of a microcontroller is determined by the amount of flash that is in a given design. And so the more dense or smaller your code is, the less flash you have to have, directly resulting in lower costs. Compressed instructions can also result in increased performance in cache-based systems. The cache is a finite resource, and if my instructions are half as wide, then I can fit twice as many of them in cache, thereby increasing performance. And one thing we do want to highlight is that the RV64, the 64-bit implementation, can also use the C extension, so you can have 16-bit instructions in a 64-bit architecture. And this is something that is not common in other architectures. And so using the compressed instruction set, RISC-V is now the smallest ISA for both 32 and 64-bit systems. And in this benchmark here is used to highlight that. So this is spec 2K6, run on a number of different architectures with GCC, using the same compiler options between all architectures. And you can see that the RV32C instruction set compared to the standard RV32I compresses quite nicely. So we have a 40% gain here over the standard 32-bit instruction format. And not only are we better than most architectures, but we're also better than the ARM Thumb2 instruction set, which is another hybrid 16 and 32-bit instruction set. Now this graph is showing the 32-bit architectures, but if we move to the 64-bit architectures, the RISC-V lead grows even further, because as I mentioned before, the 64-bit instruction set is also able to compress to 16-bit instructions, giving RISC-V a substantial lead compared to other architectures. All right, let's take a look at the atomics extension. So the atomic extension adds support for atomic memory operations, which perform a read, modify, write in a single atomic instruction. And so these instructions range from logical to arithmetic, as well as swap instructions. It also defines acquire and release bits for release consistency. And so the classic example of this is going to be a spin lock. So for example, we can use an AMO swap operation to gain access to a spin lock, and we would use the acquire bit to prevent other threads from also accessing that lock. And then after we finish our critical code section, we will perform another AMO swap, this time setting the release bit to then allow other threads to access that lock. We also use this in the SiFive peripherals, for example, for gaining access to FIFOs atomically. RISC-V also defines load, reserve, and store conditional pairs for more complex atomic operations, and it also has a procedure defined in the ISA specification that guarantees forward progress for short program sequences. Fence instructions. So fences are used to enforce order on device I/O and memory accesses. And so the fence instruction format is going to be, you first define a predecessor and then a successor, where predecessor and successor define the type of memory operation that you want to protect with the fence. And the classic example of this is going to be a producer-consumer model, or maybe we have a producer that is writing out to memory, and then it is setting a flag which tells the consumer to then go and consume that data. As the flag might be in a separate memory region altogether, the consumer might receive that flag prior to the producer's data actually being written all the way out to memory. In this case, you can use a fence to guarantee ordering that all the producer loads and stores are observed in the system prior to the consumer actually receiving the flag. All right, CSR and ECALL instructions. So CSR are control and status registers, and they have their own dedicated instructions, and we'll cover the CSRs in the next section. But just for your information, the instructions support everything you would expect. So read and write operations, as well as atomically setting and clearing bits. Environment call instructions are used to transfer control to an execution environment, as well as changing privilege modes. And so ECALL instructions trigger a synchronous interrupt. We'll talk about this when we get to interrupts. A classic example of this is a user mode application might trigger an ECALL, might issue an ECALL instruction to transfer control back to the operating system kernel. All right, let's take a look at the RISC-V control and status registers, or CSRs. So CSRs are registers which contain the working state of a RISC-V machine. CSRs are also going to be specific to a mode. So for example, machine mode has about 17 control and status registers, not counting the performance monitor registers, which add another 5 or 6. Supervisor mode also has a similar number of CSRs, although most of these are going to be subsets of their equivalent machine mode CSRs. Machine mode, being the most privileged mode in the system, also has access to the supervisor CSRs, so that it then can set the state of the supervisor mode. CSRs are going to be fully defined in the RISC-V privilege specification, but we will cover a few key CSRs here. So there are a number of identification CSRs. So the first one being the MISA CSR. The ISA naming string that we talked about early on in this presentation is also defined in the MISA CSR. MHeart ID, or the machine heart ID. So before I describe this one, I think it's important to describe what a HART is, as this is the first time we mention it in the webinar. So the RISC-V specification defines a HART as a hardware thread. A hardware thread, for the purpose of this webinar, you can equate a HART to mean a single core. So where you see HART, simply replace it with core in this webinar. However, in a more sophisticated RISC-V implementation, it is possible for a single core to implement multiple hardware threads, and this is where the HART term comes in. But again, for the purpose of this webinar, please equate HART to mean core. So the mHART ID CSR tells software the ID of the HART that it is executing on. So in a multi-core implementation, you could use this register to determine which core the software is currently running on. There are also a number of identification CSRs that are used to identify the manufacturer of the RISC-V part that the code is running on, as well as additional CSRs to give you more information about that implementation. Machine status CSR is probably the most important CSR, as it keeps track of and controls the HART's current operating state. And so the least significant bits in this CSR are used to enable or disable interrupts. So as you can see, you have interrupt enables bits for user mode, supervisor mode, and machine mode. As we stated earlier, a given implementation doesn't have to implement all three modes. So in the case where you only implement machine mode, you would only have access to the machine interrupt enable bit and not the supervisor or user interrupt enables. So these fields in the mstatus are used to globally enable or disable interrupts. When we get to the interrupt chapters, we'll talk about another CSR that gives you more fine-grained control over which interrupts are actually enabled or disabled. The next couple of bits are the previous interrupt enable bits, and these are used to store the state of the interrupt enable bits whenever you take an interrupt. So on interrupt entry, the interrupt enable bits are copied into their previous interrupt enable. And the purpose of this is so that when you restore a context, you're storing interrupt enables to their previous state. Similar for the previous privilege bits, so SPP and MPP. So when you take an interrupt, you can interrupt into either supervisor mode or machine mode. And SPP and MPP fields are used to encode which mode you came from. So in SPP, if you interrupt to supervisor mode, you either took that interrupt from supervisor mode or user mode, in which case you can encode that in a single bit. If you take an interrupt into machine mode, you could have came from machine, supervisor, or user modes, in which case we use 2 bits in MPP to encode that. Moving to the table on the right, the FS fields and XS fields are used to store the state of the floating point register file, as well as any user implemented extensions register file. And the purpose for this is on a context switch, saving register files can be costly in terms of performance. And so you would only want to do so where absolutely necessary. And these fields would tell you if you need to or not. The modify privilege or mpriv field name in mstatus allows you to access memory as if you were a different privilege mode. And this is useful if you're in machine mode and need to access memory as a supervisor or user mode. The rest of the bits in this CSR, we're not going to cover in any detail. They're really used for implementing support for virtualization. And so if you are interested in that kind of thing, I would suggest that you go read the RISC-V privilege specification. Next up, we'll talk about the timer CSRs. So the RISC-V architecture defines a requirement for a real-time counter, which is exposed as a memory map register. And this CSR name is called mtime. So there is no frequency requirement on this timer. However, it does define that the timer must run at a constant frequency so that it doesn't change during the operation of the program, and that it also must expose that frequency. Typically, this is done through a BSP or a header file of some sort. And so this is useful for operating systems and real-time operating systems, so that it gives the OS a consistent way to access time, for example. The mtime compare register is another memory map register, and this is used to trigger an interrupt whenever the value of mtime compare is greater than or equal to the mtime CSR. And we'll talk about the specific interrupt that generates in a bit. All right, supervisor CSRs. So most of the machine mode CSRs have supervisor mode equivalents, and these would be used to control the state of a supervisor mode. The bit mapping of these are mostly the same as the machine mode equivalents, and the way you identify between the two is the first letter. So the first letter of machine mode CSRs have an M, whereas the first letter of supervisor mode CSRs has an S. I do want to talk about one particular supervisor mode CSR, though, as it is different than the rest, and that is the supervisor address translation and protection register. So we mentioned earlier that supervisor mode is required because it's how you implement support for virtual memory. And so I have the fields broken out in the table on the right. And so in the SATP CSR, the mode field would indicate the type of virtual memory mode you are in. So if it's 0, that would indicate that you are not using address translation. If it is equal to 1, then that would indicate that you are using SV32 virtual memory modes. This register also encodes the physical page number of the root page table as well. Okay, RISC-V interrupts. So we didn't cover all the CSRs in the previous chapter, but there are a number of CSRs that are specific to interrupts, and we'll cover in this section. So first off, RISC-V defines the following interrupts: software, timer, external, and local. So local interrupts are optional and implementation specific. And these are the interrupts that you would use to connect peripheral devices to. So this is going to be, for example, your UART interrupt. And local interrupts are great for latency sensitive embedded type applications. So there are a number of reasons why you might prefer a local interrupt as opposed to the external interrupt, which we'll talk about later. And so the timer interrupt here is the timer interrupt that we talked about earlier. So if you have, if you set mtime compare, the interrupt that it will generate is this timer interrupt. And so that the interrupts you see here are actually connected to a given heart. All right, so the interrupt cause CSR. So interrupts are defined by reading the mcause register, and this register has two fields. The first being the interrupt field, which tells you if a given interrupt was a synchronous or asynchronous interrupt, and then the exception code field tells you the specific interrupt for a given type. So if interrupt is equal to 1, this indicates that it's an asynchronous interrupt, and then you would read the exception code. And as you can see here, the exception code directly correlates with the type of interrupts that we defined in the previous slide. So the software, timer, and external interrupts, as well as local interrupts. And you can also see here that you also have interrupts specific to a given mode. So in the previous slide, we only showed machine mode interrupt signals, although if you have additional modes, you would have potentially more signals into the heart. If the interrupt field is equal to 0, this would indicate a synchronous interrupt, sometimes called an exception. And the exception code here is used to identify the type of exception. So for example, exception code 8 would indicate an environment call from user mode. So this is equivalent to the ECALL instruction that we talked about previously. Machine interrupt enable and pending CSRs. So MIE, this is used to enable or disable a given interrupt. So we talked about the global interrupt enables in the mstatus register. MIE is used to enable or disable specific interrupts. So for example, if mstatus MIE is enabled and an MIE timer interrupt is enabled, then you will receive timer interrupts. The machine interrupt pending registers are used to indicate which interrupts are currently pending. And this is useful as you can pull the machine interrupt pending register. So let's say you don't want to actually take a interrupt or a context switch for a given interrupt. You can read the value of machine interrupt pending to understand which interrupts have been triggered. Also of interest is that lesser privileged bits in the MIP register are writable. So for example, machine mode software can set the supervisor timer interrupt pending bit if it wants to trigger and interrupt the timer interrupt in supervisor mode. So then when that machine mode software switches context back to supervisor mode, it will trigger the supervisor interrupt and supervisor timer interrupt. So I only show in the table the mapping for the machine interrupt enable CSR. However, the interrupt pending CSR has the exact same mapping. So what happens on interrupt entry and exit? So on entry, a RISC-V heart will save the current state of the machine. So it will copy the program counter into the MEPC field of MEPC control and status register. It will copy the privilege mode into the MPP field in mstatus, and it will also copy the interrupt enables into the previous interrupt enable fields in mstatus. After that, it will set the program counter equal to the value of the MTVEC CSR, or machine trap vector CSR. At that point, control of the interrupt is then handed over to your particular implementation software. And so what I have here is some example pseudocode of what a typical RISC-V interrupt handler might look like. So on interrupt entry, you might push a register file onto the stack. You would read the most significant bit of the mcause register to understand if this is an synchronous or asynchronous interrupt. And then you can use the inception code field of mcause to index into a branch table, which then jumps to your particular interrupt handler function. After your interrupt routine, you would then do things in reverse order. So you would start by popping the registers back off the stack and then issuing a mret instruction, or machine return instruction. This instruction tells the RISC-V heart to restore state, and it does this by copying the MEPC machine exception program counter CSR back into PC. It then transfers the privilege mode back into, then sets the privilege mode back to what it was prior, as well as the interrupt enables, thereby effectively restoring context to where it was prior to the interrupt. Okay, so now let's take a look at RISC-V global interrupts. So RISC-V defines global interrupts as an interrupt which can be routed to any heart in a system. Global interrupts are also prioritized and distributed by something called a platform level interrupt controller. So in the graphic here, we can have multiple global interrupts entering the PLIC on the left, and then the PLIC distributing those interrupts appropriately to different parts in the system. PLIC is connected to the external interrupt signal that we talked about earlier for one or more hearts in a given implementation. So taking a little deeper look at the platform level interrupt controller, so the specification loosely defines the PLIC, and this is done for a reason, and that's because it allows for a wide variety of implementations. So first off, you can implement your PLIC to handle as many or as few interrupts with as many or few privilege modes as required for your specific implementation. And it also scales quite nicely to multi-core implementations. And so you might have a given RISC-V system that implements a number of RISC-V cores, and this could be not only cores of the same type, but cores of many different types, so big RISC-V cores, as well as small RISC-V cores. And you can have a single PLIC which is connected to all of these and can quite easily and gracefully distribute interrupts amongst them from all peripheral sources in the system. Another thing about the PLIC is that it decouples the complexity of some interrupt types from the heart. So PCI Express message signal interrupts are notorious for being quite complex to handle. And so this removes that complexity away from the core implementation and into the given PLIC. So if you need to support PCI Express interrupts in your system, then you could design your PLIC accordingly. Whereas if you have a simple embedded system that does not need to handle these type of interrupts, you do not have to implement this complexity. And so putting everything together, this is an example of a RISC-V Interrupt System Architecture, where you have potentially multiple hearts in a system, each with software, timer, external and local interrupts of their own, and then a PLIC which is globally distributing global interrupts to different hearts in the system. All right, so that concludes the webinar for now. We did have you guys ask questions live during the webinar. And so as you guys were doing that, the panelists were actively answering questions. However, they've also been picking a few for me to talk to live here. So.
Yes, right. There's all of them. We ended up answering them all, so.
Okay, so
I forgot about that.
All questions seem to have been answered in the chat, so maybe we won't be going through them live. So again, just a reminder, this is a 3-part webinar series. We just concluded the first part in this series where we discuss the fundamentals of RISC-V. The next webinar will happen on October 17th, and this is where we will introduce SiFive's own RISC-V-based Coreplex IP, and concluding the series in November with a webinar that goes through evaluating SiFive's IP. Also, for more resources, so this webinar, we will be posting the slides as well as the video of the webinar on our website, but I've also posted a few links here, which are good resources for finding more information on RISC-V. So RISC-V.org is the Foundation's website. This is where the specifications are housed, as well as links to the RISC-V mailing list, which contains a wealth of information as well. The workshop proceedings, so every 6 months or so, RISC-V has a workshop where the architecture is discussed and different member companies have a chance to present some of their technology. These are all very useful and interesting, and the videos and slides of these proceedings are published on the RISC-V.org website. GitHub, so I have links to SiFive's GitHub as well as the RISC-V GitHub. I will have RISC-V GitHub on here. As most current open source projects, a lot of the active development happens on GitHub, and this is true for SiFive as well as RISC-V. So if you actually want to get involved and help contribute to RISC-V or SiFive, we strongly encourage you to go to GitHub and make pull requests as appropriate. And then finally, SiFive.com is your one-stop shop for RISC-V-based IP, development boards, development tools, as well as our own fairly active user forum. So this concludes the... So we do have a question, what Linux operating system can the RISC-V GCC tools be installed on, and is there a list somewhere?
You may answer it? Yeah, okay. So we released our binary tools for Red Hat and Ubuntu, and there's an OS X version as well, which is not really Linux, as well as a Windows one. And I believe those are the ones we support the best.
That's right. So we have binary distributions on the SiFive.com website. In addition to that, the source code for GCC and how to build them is on the RISC-V GitHub. So presumably at that point, you could build the tool chain for any distribution of Linux. Any other questions? Okay, so another question, are there any RISC-V-based microcontrollers on the market? That is a great question because SiFive happens to have one. So we have a working RISC-V silicon since November on a part that we call the FE310G000. Currently, we sell this silicon as part of the Hi5 development platform, but I'm glad to announce on this webinar that we also will be making this silicon available without the board through crowd supply in limited quantities. So stay tuned. I think we'll have an announcement on this in the coming days. Checking for more questions. Does the GCC compiler target both the user and privilege instructions? The answer to that is yes. For a lot of the CSRs, we mentioned that they have instructions, their own instructions, and so there are a lot of macros defined to actually read and write the CSRs, but these header files, these macro files are available on SiFive and RISC-V's GitHub. All right, I think we're going to conclude the webinar now. So I'd like to thank everyone for joining, and I look forward to having everyone attend on the next webinar.